auf Stahnsdorf vor. Der Feind operiert jetzt am nördlichen Stadtrand zwischen Frohnau und Pankow und im Osten ist der Feind bis zur Linie Lichtenberg-Marsdorf-Karlshorst gelangt.
Mit dem Angriff Steiners wird das alles in Ordnung kommen.
Mein Führer, Steiner
konnte nicht genügend Kräfte für einen Angriff massieren. Der Angriff Steiner ist nicht erfolgt.
Es bleiben im Raum Keitel, Jodl, Krebs und Burgdorf. Das war ein Befehl! Der Angriff Steiners war ein Befehl! Wer sind Sie, dass Sie es wagen, sich meinen Befehl zu widersetzen? So weit ist das also gekommen. Das Militär hat mich belogen! Jeder hat mich belogen, sogar die SS! Die gesamte Generalität ist nichts weiter als ein Haufen niederträchtiger, treuloser Feiglinge!
Mein Führer, ich kann nicht zulassen, dass die Soldaten, die für Sie verbringen...
Nicht als Feiglinge! Verräter, Versager!
Mein Führer, was Sie da sagen, ist ungeheuerlich!
Die Generalität ist das Geschmeiß des deutschen Volkes! Sie ist ohne Ehre! Sie nennen sich Generale, weil Sie Jahre auf Militärakademien zugebracht haben, nur um zu lernen, wie man Messer und Gabel hält! Jahrelang hat das Militär meine Aktionen nur behindert! Es hat mir jeden nur ersichtlichen Widerstand in den Weg gelegt! Ich hätte gut daran getan, von Jahren alle höheren Offiziere liquidieren zu lassen, wie Stalin! Ich war nie auf einer Akademie. Und doch habe ich allein auf mich gestellt, ganz Europa erobert. Verräter! Von allem Anfang an bin ich so verraten und betrogen worden. Es wurde ein ungeheurer Verrat geübt am deutschen Volke. Aber alle diese Verräter werden bezahlen. Mit ihrem eigenen Blut werden sie bezahlen. Sie werden es saufen in ihrem eigenen Blut.
Bitte, Gerda. Jetzt beruhig dich doch.
Meine Befehle sind in den Wind gesprochen. Es ist unmöglich, unter diesen Umständen zu führen. Es ist aus. Der Krieg ist verloren. Aber wenn Sie, meine Herren, glauben, dass ich deswegen Berlin verlasse, irren Sie sich gewaltig. Eher jage ich mir eine Kugel durch den Kopf. Tun Sie, was Sie wollen.
Hello everyone, welcome back to another video in Zeta and Theta Maths. So, today we will be doing some binomial expansion, as you can tell in this very fun and really cool video. So, I promise it won't be boring, that's number one. But number two, we'll certainly be looking through this example right here, right now. So, you'll be asking what binomial expansion is and what it's used for. Well, here's a really nice use for binomial expansion. So, if it ever asks you to expand, say, like an expression. So an expression can simply include anything that's algebraic. So this is algebraic because it has a very cool x in its term. So The whole idea of binomial expansion is that, well, usually when you have some more simple expressions, so let's just go to the side right here, and say you had 1x plus 1, for example. And now let's say it's squared. Now, if you're a seasoned math student, you'll know that when you have x plus 1 all squared, what happens if you just simply get this, x squared plus 2x plus 1. Now, the reason why I'm showing you this is because there's a trend. So let's say we have this same expression, but let's just mark it as a bar and put it all cubed. We know that that's just going to give you x cubed plus 3x squared plus 3x plus 1. Now if we keep going,
Oh my God, bro. Oh, hell no,
the following, so as you'll see here again, if I do this to the power of 4, it's going to be x to the power of 4, then we're going to have plus 4x cubed plus 6x squared, and then there's going to be another plus 4x plus 1. Now notice how it gets ever so longer and ever so more difficult to expand all these three expressions right over here. Notice how difficult it gets. So I actually remember this, and the reason why it's so easy to remember is because if we start off with an expression, say x plus 1 squared, well, what we notice is that the coefficient of this x squared term over here is just 1, the coefficient here is 2, and this is just a number on its own, so it's 1. Notice that it just follows like a pattern. This goes 1, 3, 3, 1, and this goes 1, 4, 6, 4, 1. Now, a very famous guy, his name was Blaise Pascal, and what he noticed is that if we take all this jargon we had over here, what we can do is form a little triangle. And I think it's a really nice idea because say you're looking at an expression and you can't really be asked to expand it all out. What mathematicians generally really enjoy doing is just simply either remembering these all little sort of tricks, or we just sort of form a little sort of, I guess, I wouldn't say empirical model, but something that just makes it so much easier to work with instead of having to always expand something out. Alright, so this thing that I've just drawn here is something known as Pascal's triangle. Now, Pascal's triangle basically just says if you have an expression such as, for example, x plus 1 over here, then we'll just say that it's going to be 1, because that's the only coefficient we sort of have. If you have x plus 1 all squared and you finally expand this all out, so remember, x plus 1 squared, so expanded out, these are the following coefficients you end up having, of course except from that 1. If you expand x cubed out, you get 1, 3, 3, 1. Expand this out, it goes 1, 4, 6, 4, 1. Now, the whole idea is that, well, if you look very much more closely, so let's just zoom in, what we notice is that these ones just stay the same along these sides. So the one, I like to say, it's like a protective barrier, it's protecting these little numbers in here. But when you take 1 plus 2, you look down this way, it gives you 3, 1 plus 2, 3, and this makes it very easy to predict sort of what the next number is. So in this case you have 1 plus 3 and now it's 4, 3 plus 3 is 6. 3 plus 1 is 4. And now you can do this again by simply adding these up, these up, these up. So using the same method, what we can say is we're going to have 1s over here. Then if we do 1 add 4, it's going to give you 5. 4 add 6, 10. 6 add 4, 10. And 1 add 4, 5. So essentially the reason why Pascal's triangle is really cool is because then what he did is he did this thing, and when I'm sure all of you at some point have looked at your calculator, have seen something that looks like this sort of button that looks on your calculator. So let's just square this off. Actually, let's put a little squawk around it because that's what it actually looks like. But I'm sure you've all seen a button that looks like this on your calculator. Basically, to explain it very simply, is that n is simply your row, or actually your power sort of, in your Pascal's triangle. So say we have, for example, a power of 2. That would be your n. So let's say n is equal to your 2. And your r very simply means, well, which part are we looking in that triangle, in that part of the triangle. So in this case, let's say we want 2, C, and C is just another word for choose. So it's just 2, choose, and then, for example, let's put 1. And so let's see, 2. This is our second row, so that's going to be our 2. Choose. What are we choosing in that row? Well, we're going to be choosing the first sort of part of that number in this row. So we're choosing 1. So this is our first part in this row. So we clearly know that's going to be 1. So in this case, if we're saying, for example, 5, now we're going to do 5 because we've just done 5. Let's say we do choose 3. 5 choose 3 is, because it's to the power of 5, it's going to be in this section. We're choosing the third one in this row. It's going to be here. So it's going to be 5 choose 3 is 10. And what we can also very sensibly say is it's the same as 5 choose 4. Why is it 5 choose 4 equals 5 choose 3? Is because it's the same. It's the same number in this row. Because we remember we've done 4 add 6 is 10, 6 add 4 is 10 again. So that's absolutely fair. You can do that anytime. So this is a valid sort of thing to say right over here. And you can also say 2 choose 1 is also 2 choose 3. So let's just put an equal sign, 2 choose 3. Now that we've gotten all this out of the way, we can now go back to our original question. And it's how can we expand this to the following expression for the first 3 terms? Now you'll understand why I've sort of introduced you to these choose this, choose that, because it's to the power of 20. So a very important thing to notice about this is that because it's to the power of 20, it's going to be 20 choose a digit. So if we're going to choose to expand this out, we have to also know a rule. So just before we put an equal sign, I'm going to introduce you to a very, very nice rule that you should know. You should know by heart. You should be able to literally just regurgitate it out, like throw it out of your mouth, and it will be very slick. So say we had that sort of A plus B X, and it was to an nth term. Now we know that n is 20 and that your B was, I believe, 3 and your A was 1. But let's ignore that for a second because that's not what we're trying to explain. So your A, first off, what you begin with, is your a to a power of n. Very simple. That's your beginning. Now, what do we do next? Well, if we wanted to the first three terms, that's your first term, so that's very good. Your first term, that's valid. Actually, let's do that in green. Bruh. That is valid. Now your second term is going to be your n, choose a number. That's why I introduced you to that. So your n, choose a number. So in this case, it's going to have to be 1. So let's just redraw that. So it's going to be n, choose 1. Now, we're going to multiply this by your a again, but it's going to be now n minus 1, because it's your next power that we're looking for. And then we take this and we multiply it again, just by b. Just by b. It's to the power of 1. Just by b to the power of 1. Now, this is your second term. Oopsie daisy. Let's just write that again. This is your second term. Now, your third term is simply going to look like this. Now you add on your third term, and your third term is going to be n choose 2. Because we're looking for the second part of that row, we were looking at that Pascal's triangle. So it was the nth part of that row. So now that we have this, we then multiply again, but this time by a n minus 2. Minus 2. So whatever that n is, you subtract it by 2. And in this case, you just increase the power of b by 1. So you add on 1. So b is going to be 2. And now you can just keep on going with this expression. So it's going to be a dot, 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 and ellipses. And then what's going to happen is that you can keep going until this binomial expansion is finally finished. So in this case, say we have just now at this point, it's going to be n choose now a random sort of point at which it now finally ends. And what this would mean is simply it's going to be a, and that's going to be to the power of n and whatever this is. So if this was your final number, say it was like 4, because it's about 4, you subtract it by your r. And at this point your n and r would match with one another, and this would give you 0. And you add on your final whatever b to the power of your final power. So if it was all to the power of say 4, as we said before, you multiply it by that. Now this is only true for all natural numbers. So n only works for all natural numbers. So you never want to do this with, say, a real number. Now it sort of does work with real numbers. The whole point is that, well, a real number could be 1.5, and a real number simply means something that exists. So it's not imaginary, it's real. So it's not like the square root of -1. It's a real number. It exists. And these sort of have some similarity between each other, but it's important to know natural numbers. It only works for that. So natural numbers simply mean just counting numbers. So it can include 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So I'm going to just rub this out so I don't confuse any of you all. It only works with natural numbers. Very important to remember, natural numbers. So, whoops, natural numbers. So if we go back to our original question. Now we finally know what to do. I hope I haven't lost your attention. Okay, so a few things that we like to do just before we begin at the start is we're going to say what our variables are. So when we're expanding using that a plus b all to the power of n formula, what we had was sort of our a. So for now, what we're going to say is our a is 1. Our a is 1. Let me just correct that a little bit. Our a is 1. So our b, in this case, we're going to say is 3x. 3x. Now our n is going to be 20. Now, I know what you're going to be asking. Zeta, theta, maths, what's the point of doing this if I can just like do it in my head? Well, sometimes it's for beginners, for rookies, like I like to say. It's a little bit more difficult to follow a rule like this. So it's sometimes very nice to, well, just label our stuff, make sure we don't make any mistakes, do it slowly. But once you really start getting into the hang of it, then you can just start really getting at it. So what we're going to do for now is we're going to just select this and we're going to make this a little bit smaller, just so it's not in our way. So yeah, right here. So let's see. Let's take our brush. Okay. If it's going to be equal to something, well, first off, remember it was a to the power of something. So we're going to have 1 to the power of 20. That's really cool. That's very easy to resolve. So that's one part done. We're 1/3 of the way through. So now we'll add. What are we going to add? So if you remember when I introduced you to the thing, choose thing majig, we're going to do 20 because that's a power and it's what our n is. Choose. I'm going to choose 1 because that's what we're looking for. It's our first part of that row. Now you might be asking, well, what is 20 choose 1? What is that? Just look up on your calculator. But because I'm so smart and really cool, I know that's just going to be 20. But just for the sake of following the rule, we're going to just put 20 choose 1. Now we're going to multiply this by a, and our a, remember, was 1. So it's going to be 1, but it's going to be to the power of 19. Now again, you don't probably really have to put 19 in this case, but because we're following the rule, we're going to put that there, and it's good for beginners just to do that as well. So you really get into the hang of it. So 20 choose 1, 1 to the power of 19. Now we're going to do b now. Now our b is, in this case, it's just going to be to the power of 1. So it's going to be left as 3x. So we're going to leave it as 3x. See how I've done that really majestically. 1 to the power of 20, that's alright. Now we've got 20 choose 1, that's going to be 20 in the end, but that's okay. It's going to be 1, and that's going to be 3x. So at the end, what we're going to get is we're going to get 60x over here. So I'm just going to do this. It's going to be 60x. Now, for a final term of this sequence is we are going to do 20 choose 2 first. Now I'm not going to explain why that is. This is just the second part of that row that we're looking for. Now I actually don't know what 20 choose is. 20 choose 2 is, but again, calculators are there for a reason, and it's one of the reasons why I really recommend to get used to your calculator, because if you don't, it gets very difficult. So that's 20 choose 2. Now what is our going to be a? It's going to be minus 2. Remember we had a, n, minus 2. Our n is 20, 20 minus 2, 18. So our a was 1. It's going to be to the power of 18. Now again, you're all going to scream at me for putting 1 to the power of 18. I know it's just going to be 1. The whole idea of putting that like this is so that any rookie beginners know what they're doing. So 1 to the 18, and now we're going to do our b, but it's going to be now to the power of 2. It's going to be to the power of 2. Now we're going to put plus, I'm going to put an ellipses, or otherwise what people often like to call is a dot dot dot. Now this just shows to the examiner that you you could expand it all out, but you're really smart and you don't have to, and that you know that it's just to only 3 terms, like it says here. Only 3 terms, nothing else. Now the next part is to resolve it. Now I've resolved the part for you, but hopefully I think you can do this by yourself now. But you can pause the video and do it yourself, but if you're lazy, then I'll just do it for you. So if you put 22 into your calculator, that's just 190. 190. Now that's going to be multiplied by 1. 1 to the power of 18 is just 1. And this, well, it's all to the power of 2. So given that we know our algebraic rules, anything in our brackets, because this is 1, that's going to be 1 times 2. So that x is going to be squared. 3 squared. 3 times 3 is 9. So we know that this is going to be 9x squared. 9x squared. This is going to be. Now let's just put a little imply symbol, and this implies that the answer to the 3 terms is going to be 1 plus. Now look back like I'm going to my page. 190 times 1 times 9. Now 190 times 9 is just going to be 1710, and that's going to be x squared, and we already know that we have our 60x still remaining, so let's just add on our 60x. I know I've done this sort of the opposite way around, usually put your x terms first then your x squareds, but also this is all to the power of 20, so not going to fully expand that out. Nobody would expect you to probably expand all the way to 20 terms. I mean, any very skilled mathematician should know how to expand it to all 20 terms, but I honestly really doubt they'll do that to you, because they'll try to make these papers as accessible as possible, and what that basically means is they'll just make it easier. So they'll just sort of give you that and expand it to these terms, and even sometimes they might give you sort of like a question to sort of answer to what, maybe do an approximation, which is also a very common thing. So yeah, that's one thing. So that's how you expand it to the first 3 terms. Essentially, when we look into an expansion like this, sometimes as a part B, so let's just do this very quickly. Part B, they might sometimes ask, for the following expansion of 1 plus 3x all to the power of 20, for what set of values is x of this expansion valid for? So a very simple way of going about this is to just say, well, okay, we know this is completely valid, we know that this is true, and therefore, because this is true, we can now say that 1 plus 3x is less than 0. Now it has to be less than 0, because if it's greater than 0, then, well, clearly this is going to be wrong. This cannot be less than 0. So then what we can say is, okay, so for this set of values, because it cannot be less than 0, we can now have to say that because it's less than 0, essentially, that this is going to have to be in a modulus. Wait, let me just draw that modulus very sharply again. Okay, this has to be in a modulus because, as I said, this can't be less than 0. This wouldn't make sense because this is these will only give you positive values in this case. So this is going to have to be less than 0. Now, you just solve it for x. So essentially what you do is say, okay, if we know our algebra and you did the very famous ladder rule, I'm not going to go through that, that's some GCSE garbage, but you know what I'm talking about. So 3x modulus is less than minus 1, because we took that 1 and we plunked it over to the other side. Now essentially, well, just divide by 3, so then we end up as getting x, which is less than minus a third. That's pretty much it, and that would just simply be your answer to the following part B. I think that's pretty much it for this type of question. Let's move on to another example. Okay, so now we're going into some year 2 topics. Now, you might be looking at this and going, zeta theta maths, how the hell am I going to do this? This is insane. The square root of 3 plus 5x, how are we going to fully expand this? Now, I'm going to answer your second question first. We are not going to fully expand this. We're going to expand it to 4 terms. Now, if any of you have been doing some of your research, and I hope you have, you will know that this sort of expression that we have represented here will be an infinite binomial expansion. It will never come to an end. It will just keep expanding and expanding and expanding. It will be like a sort of like a beanstalk that just keeps growing and it never comes to a stop. Or just sort of a rat infestation. It just keeps growing and growing, and until all the food out of your house is gone, it just won't stop. Anyway, the whole idea is that it's an infinite sort of expansion. So first rule, well, was another way of writing this expression as? Another way of writing this expression as is by simply saying, okay, equals, we're going to say it equals, and yes, I'm using a blue marker, guys, very happy. So this was 3 plus 5x, but now, because it's 3 plus 5x, we all know that this can be also represented all, come on, what is it, to the power of half. Not a very engaging audience here. No, I'm just kidding, you can't talk to me, I'm not crazy, don't worry guys. But anyway, it's just 3 plus 5x, all to the power of a nice half. Now, we cannot expand this using our regular... So you remember, guys, when we had this sort of formula where we said a plus b, and it was all to the power of n. Yeah? We remember that? If we do, great. But the whole idea is that you cannot use this formula for anything that has an n to the power of a half. The reason why you cannot use this to anything to the power of half is because it is not a natural number, as we said before. And because it's not a natural number, we cannot use this expansion at all. So we're just going to cross this out. We cannot use this particular expansion. Now that's sort of, I guess you can say, the bad news. But for the good news is that we have another rule that we can use, and the other rule you can use for any real numbers. So we're going to write it in these sort of big, sort of bold letters. They use these on an exam in like a really nice print, and you've got to get used to recognizing these, because if you don't, then you're going to be in a whole world of trouble. Anyway, for real numbers, what you can say, so let's just put this. So for real numbers of x, you can use a different expansion. So I'm just going to scroll right down here to show you what type of rule we can use, and that's completely valid. So say we have an expression of 1 plus x. So just 1 plus x. Very simple expression, 1 plus x. Now, what power do we want it to? Because it was to the power of a half in the previous sort of example that we're going to do, let's sort of do this also to the power of a half. Or, of a matter of fact, let's just use n in this case. Now, you're going to know why I put 1 plus x again in a moment, but first thing we want to do, when we expand this, and this has a 1, we don't have to take out any numbers, we don't have to play with it or anything. This is all ready to go. And you understand what I mean when I will do the next example. So we have 1 plus x to the power of n. So first thing we write 1 plus. That's already one part done. So I guess if we're going to expand this also to the first 4 terms, like it says here, I guess this is we are a quarter way done. And you've just written 1 plus. Amazing, right? So that's already correct. Now, the next thing you got to do is you got to say x, and then you got to multiply it by n. And you might be asking, zeta theta maths, is this true for all expansions that you do when it's to the power of, say, a random sort of real number? Yes, it's always correct for that. It's going to be 1 plus whatever x is, so it could have a coefficient like 3, 4, 5, whatever, and multiply that by n. Now, after that, because we are now looking for an x squared term, this is where it gets really funny, and I hope you've done your research on factorials as well. And if you haven't, well, you're going to learn about them now. So, let me just draw a little line over here. So, come on. There we go. So, once this loads, okay. So now, what you have to do is say, and that this is very important you get this right, n. You write n, and you multiply it by n minus 1. That's not it yet. We're looking for the way how I like to think of it, because we're looking for an x squared term, you have to have an n minus 2, because it's squared. Okay? So n minus 1, n minus 2, this is true every time. Just like xn, this is true every time. Now, good news is that we have that, and that, which is nice, and then whatever your this part is, so say it had a 3 inside, you'd put in, you go here, and you'd put x, or say 2x, and you'd square all of it. So it's similar to your average binomial where you had it to your 5, and then when we had that b term, we'd square all of it. Similar to this, we square all of that inside. Now, again, the way how I like to think of it, because we're looking for this x squared term here, this is going to be beneath it 2 factorial. Now, it's important you put that factorial in, because factorial just means 1 times 2 in this case. That's 2 factorial. But say we had 3 factorial, that would be 1 times 2 times 3, and that will just give you well, I mean, this is 3 factorial, but this is also equal to 6. And now this goes on and on. 5 factorial gives you, I think, 125. I'm going to put, if that's wrong, I'm going to put what it actually is. But the whole idea, factorial of 6, well, no, it's 120. 5 factorial is 120. I'm really sorry, guys. I was thinking of 5 cubed. But that's not the point. 2 factorial, 1 times 2, 3 factorial, 1 times 2 times 3, 6, whatever. So that's basically all that means. So I'm just going to box this off and put it right into like a little corner just to remind us what to do. Now, honestly, guys, when you do your revision, I recommend you do that too. When you need a fact, just sort of, I wouldn't say box it off because you're probably using a piece of paper. And if you're not using a piece of paper, you're going to always get distracted by a computer. So that's the whole idea. Now, again, when we use this rule again, because we're not looking 1, 2, 3, now we're looking for a 4th term. So when this loads again, we're going to do another plus, and now we're going to be looking for an x cubed term. So our x cubed term is, again, it's going to be a fraction, and okay, you're going to load, thank you. God, I'll never understand this computer, but I'm going to have 3 factorial, And just as I said before, 3 factorial is just 6. But we're going to leave it as 3 factorial because it reminds you that it's going to have an x cubed term. So again, you're going to have your n, but because we're looking for that cubed term, not only are we going to have n minus 1, not only are we going to have an n minus 2, but guess what? Because you're such an engaging audience, you're probably screaming at me, Zeta Theta Maths, it's n minus 3. And you'd be absolutely correct. Well done. Thank you for your help. But I'm not crazy. I promise you that. But the whole point is now, because we're looking for that x cubed term, and again, if we had, say, an integer as well attached to that x, so it's 3 times x, you'd cube it all together. Now, that's how you'd find your 4th and final term. So again, very important reminder, this, let me just change to something really nice. This would be your first term, which is correct. This would be your second term, which is correct. This would be your third term, and then your 4th term. Now, basically, you might be then again asking, Zeta Theta Maths, how do you find your 4th term, for example? You do the same, no, I mean, your 5th term, yeah? So, your 5th term would be x to the power of 4, but instead of n minus 1, n minus 2, n minus 3, you now have an extra n minus 4. Now, they very rarely ask you to go all the way to an x to the power of 4 term, but that's all you have to do. So, now that we have our 4 terms all nicely laid out here, we can now use this very delightfully with this. So, given that we have that, and we have to the power of half, oh wait, I think I forgot to say something. This only works for 1 plus x, so it has to be plus, and it has to be 1, because other than that, this will not work. So it's to be 1 plus and then something. Now, I'll probably check if it has to be a plus because I can't remember right now, but I'll probably put in subtitles somewhere, but I'm very positive that it has to be 1 plus x positive. See what I mean here? I've got a positive. Anyway, you don't like my jokes anyway, so I'll shut up and do my thing. So, let's go back to our original question after we reviewed our sort of second year binomial expansion. So 3 plus 5x. Or you might be asking, Zeta Theta Maths, how do you get in 1 plus a thing? It's very simple. If we know our indices laws, all you can very simply do is say that that is equivalent or identical, for the matter of fact, of saying 3 to the power of a half multiplied by 1 plus 5 over 3 to the power of a half. Well, x. Let me just block in an x. That would have been tragic if I didn't put in that x. That x has a livelihood and it needs to be fulfilled. So it's 1 over 2. Now, the whole idea is that, say I were to put this back in again, 3 times that, okay, it's 3, it's all to the power of a half. In fact, I'll just rub this out and put it all to the power of a half. Very important, it's all to the power of a half. This 3. 3 to the power of half, we multiply that back in, okay, that's fine. And remember, when we do 3 times 3, these 3 cancels and you get your original 5x back. So this is valid, but you have to ignore that little 3 here for a bit. It has to be ignored, and it's, you know, it's going to be a little bit lonely, but it's okay. It'll be back in a minute. But what we're focusing on is how to expand this to the first 4 terms. So let's expand that. So the first thing we're going to do is, yeah, we're going to have a 3 here, but it's going to be on its own for a bit. And then what we're going to do is follow that same rule that we had right down here with that 1 plus xn nonsense. Well, it's not really nonsense because you're gonna need this. So, well, I'm explaining to you for this for a reason. So it's gonna be 1. So first term 1, second term xn. What was our x? It was 5 over 3, and 5 over 3 times by a half is just simply 5 over 6. 5 over 6x. Now, we're going to write that as 5 over 6x plus, what do we add on again? Oh yeah, remember we're looking for an x squared term, so the first thing we're going to do is we're going to draw our little line here, draw a long line. Now draw your fractions. Every time you do fractions, draw your fraction line first, because it sort of, you know it's going to be a fraction, so just draw a fraction line. So we know it's going to be a square term, so we're going to put 2 factorial. 2 factorial. We know it's going to be just 2 factorial is 2. That's not the point. We remember that it's going to be a square term, so it has to be 2, because it's to the power of 2. So, what's your n? Your n was, remember, a half. So we're going to do a half. Now we're going to multiply this half by a half minus 1. So that's going to be a half minus 1. What was it, guys? Half minus 1? Minus a half. But given that we want to follow this rule, I'm not going to skip right ahead just yet. Now, already we know this is going to be negative. Now, I'm going to have to do a half minus 2. So, come on guys, what's a half minus 2? So if you know a half minus 1 is minus a half, minus 1 again, that's minus 3 over 2. But we're not going to do that just yet, because, you know, we're looking for an x squared term, and we don't want to rush ahead. Oh look, it's going to be all 5 over 3x. Now, it's going to be all squared, as I said before. When you have that coefficient in front, 5 over 3x, and it's going to be all squared, just like we said before. Now, we're looking for sort of four terms. We're looking for our fourth term. So now we're going to be looking for an x cubed term. Now I know this is getting very long, but it's important that you know how to expand this fully. Let's expand this all to the full 4 terms, so you get all of that, most of the time 7 marks that you're looking for in that question that asks you for that binomial expansion. And these binomial expansion questions, if you remember this like I've remembered it right here as I'm showing it to you, it ends up being very easy and very just straightforward. You get very easy marks and you end up getting an A like me. So again, n, a half minus 1, and we know what a half minus 1 is, but we don't want to rush ahead. I want to show you how it's done. A half minus 2, because remember our n is a half, you subtract it from 2. But remember, we're looking for that x cubed term, so we're going to put in another half minus 3, because it's to the power of 3, isn't it? So a half minus 3, then, you know, that's minus 5 over 2, but it's okay. And then 5 over 3, and it's going to be x, and it's going to be all to the power of 3, because we're looking for that x cubed term. It's kind of slipping off the edge here. We're going to save it. Now, it's 3 factorial, because remember we're looking for that power of 3. Okay, so we've sort of blotted in our numbers into the equation that we were looking for. Now we're going to bracket this off because it's all going to be multiplied together. But just before we do anything, let's resolve. So, if you are very, let's just say, skeptic of what you're looking for, we're gonna have to sort of you can just put this into your calculator, but we're gonna do this out loud one by one, just so we know what we're doing. So first thing it's very nice to know is that this is going to be negative, this is going to give you a negative, and this is going to give you a positive. So negative times negative, positive. Okay, so this is going to be overall, this entire thing is going to be positive. So we will need, so whether we or not, we need to change our sort of integer. It doesn't matter. So it's given that this is going to be positive, we already know that, okay, half minus 1. If you don't know how to do a half minus 1, do it on your calculator. It doesn't matter. If you know how to quickly use your calculator, all the best for you. So half minus 1, I already know it's minus a half. So what's going to happen is there's going to be a half, and then it's going to be times by minus a half, and then that's going to be multiplied by a half minus 2, and a half minus 2 is just going to be minus 3 over 2. Now, if we know what 5 over 3 all squared is, this is going to be very easy. This is going to be then multiplied by 5 squared, that's just 25, and under here is going to be 9, because 3 squared is 9, and then it's going to be all x squared. And this is all divided by a 2, because 2 factorial is 2. And again, I know I'm doing this all mentally, but I'm purely doing this just to show you where this is coming through from. So these are going to be positives. So I guess you could do this now on your calculator, but so a half times a half, that's going to be a quarter. A quarter times by 3 over 2, that's going to be 3 over 8. 3 over 8 times by 25 over 9. So 3 over 8 times 25 over 9 is going to be 25 over 24. 25 over 24 divided by 2. 25 over 24 divided by 2. That's going to give you 25 over 48 all squared. So say we are now going to write this as 25 over 48, and it's going to be x squared. Now, for the next part, so we already resolved this. We've already resolved this. And we've nicely resolved this. Now there's only there's only one part to go. See what I mean? Look how quickly I've done this already. And this is how useful these formulas are, and how much I encourage you to learn these by heart, because these questions can end up being very, 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 very easy. So again, let's go through this logically and mathematically like mathematicians should. So going through this, well, what do we know about this? That's going to be negative times negative, positive. Positive times negative, negative. This is going to be an overall negative. So a half minus 1, that's minus half. So that's going to be first off half. Let's just zoom in real quick. Times by minus a half. Now, given that's times minus a half minus 2. A half minus 2, that's going to be times by minus 3 over 2. Now, given that's times minus 3 over 2, we know that that and that is going to give you a positive. But now, a half minus 3, I believe, is minus 5 over 2. It's going to be times by minus 5 over 2. Now, we're going to times this by 5 cubed, which is 125. Let's just put this here. And 3 cubed, which is 27. So 27 x cubed. Okay. Now, this is all over 6. So let's just do our little line. It's going to be over 6. Now, let's just calculate this all up. A half times a half, a quarter. A quarter times by 3 over 2, 3 over 8. 3 over 8 times by 5 over 2. So 3 over 8 times by negative 5 over 2. Let's be very specific. Minus 15 over 16. Now, minus 15 over 16 times by 125 over 27. What that's going to give you is something along the lines of this. Minus 625 over 144. And that is going to be divided by 6, and which it will overall give you, well, this is going to be all x cubed. And if you choose to divide this by 6, you're going to get minus 625 over 864. So I was probably right in saying that you should probably use a calculator for this, because it's very nasty operations. But I guess for your final answer, when you've got to be writing down what this and that is, well, first off, you're going to just say that, well, what is our binomial expansion equal to? 4 times. If you're using your little pencil, I guess, you can just say it was 1 plus 3x, or actually cut that out. So you may believe that this is it, this is over. Yes, it's all over now, isn't it? Well, no, it isn't, because remember, we have that 3 to the power of a half still waiting at the side of your equation. So next thing we're going to do, well, we already know that that's going to be 3 to the power of a half, and that's going to be all multiplied by, well, whatever we got here. So that's going to be 1 plus 5 over 6 x, and that's going to be then add on to 25 over 48, or x squared, 48 x squared, and subtract our very nasty looking number of 625 over minus 864. Now, I made this sort of expansion up, so I have no idea why these numbers look like that. I've just expanded it like that, so it's going to look like that, unfortunately. So 3 to the power of a half is just 3 all square rooted. So I guess what you can do here is then say, very funnily, well, you're going to have your expansion is going to look something along the line this. Root 3 times that is 1 plus 5 over 6 times by root 3. 5 over 6 times by root 3 is just 5 root 3 over 6. And it's going to be multiplied by x, because remember, it's an x term. And now we're going to have your 25 over 48 times by your root 3, and that's going to be add 25 root 3 over 48. Now, anyone who's experiencing this will look at this, and this looks very hilarious, and I'm kind of smiling right now just at the look of this, but the reason why I'm smiling is because of how ugly this looks. Now, nothing against looks on this binomial expansion. It's just, you know, listen, usually they won't very much ask you to do something as ugly as that, but the whole point is that of doing an example like that is that you know where this all comes from and which rules you want to really use. So if you're really looking for your final answer, I guess this answer of root 3 add 5 root 3 over 6x add 25 root 3 over 48x squared minus 625 root 3 over 864x cubed is your final answer to that binomial expansion. So, and then again, if they'll be ever asking you, say, well, they might ask you to do an approximation, and now I'll not do an approximation question now, I might do it in another video, but what they'll also might ask you is, again, for what values of, say, 3 plus 5x to the power of half is this expansion valid? So, again, very simply, in this case, what you would do is, well, you would say that, okay, so you have your 3 plus 5x to the power of a half. So let's just write that down again. So it's 3 plus 5x, and it's all to the power of a half. So, given that it's all to the power of a half, well, the first thing this implies is that you're going to have to write 3 plus 5x, and it's going to be modulus, because it has to be like that, and it has to be less than 0. Well, it has to be greater than 0 because it has to be a positive value that's going to plonk in there to make it valid. So then what we're going to do is, of course, minus 3. So 5x, and you modulus it off. It's greater than, that's minus 3. I'm going to divide it through by 5. And then what this basically means is that your value that's valid for this expansion, well, you can, in this case, because it's negative and positive, what you can actually say is that using this rule as well, less than or equal to the modulus of x, and then you can also say is that this and that. This is also a rule that's commonly used in binomial expansion of the range of values. It can be either in this quadrant right here, or can be in this quadrant right here. Now in this case, it's probably going to be in this quadrant. It's going to be a negative value. So I know I've said before this can't be negative. It can be negative in this case because it clearly did have some negative values in here. Actually just one, because we expanded to the first 4 parts. So in this case, what we can say is that, well, replacing these with minus 3/5, and then saying it's going to be less than or equal to x, and that's going to be less than or equal to 3/5. And that is where your values of x will be valid for. Alright, this is probably going to be the final example for today. I had a lot of fun recording this. I hope you had a lot of fun watching me suffer while I try to expand all of this jargon. But I hope you had fun watching this video. I want these videos to be very fun for you all. And if you ever want to see any maths video about, say, binomial expansion, or just even simply multiplying surds together, please just throw something down in the comments below. It really does help. Also, if you comment, also please do sure to subscribe and like these videos. They'll motivate me to make more of these very helpful videos, especially since when I'm recording this, it's the 16th of September. Some of you will be in year 12 and year 13 doing maybe some of binomial expansion or whatever the hell you're doing, but I really enjoy making these videos and helping you out, guys. So I guess I'll see you in the next one. Have a fun one. Bye bye.